Right. Hello, this is the final recitation recording for CS155. The purpose of this recording is to really go over, in a very high-level overview, some of the contents that we covered this quarter in the class. And yeah, so I'm going to start by talking about a recap of the material that we did in supervised learning. In the supervised learning pipeline, we had a training data set, S, which consisted of inputs, X, and outputs, Y. And in the general framework of things, our inputs are d-dimensional real-valued vectors, and our outputs are from the reals. And this is a very general notion because even in binary classification, when your output is just 0 or 1, this is still a subset of the reals. And then we defined a model class or a hypothesis class, which was for the linear models, something like W transpose times X, which is just the dot product of your weight vector W and your inputs X. And then we defined a loss function, L, of Y and Y prime, which measures the deviation between your target vector and your predictions for the target vector. We spoke about different measures of the loss function, but the main one that we talked about was squared loss, and I'll also go further to define some of the other loss functions. And these three ingredients above define the learning objective, which is, can we find the weight W that minimizes this loss function of your target vector, yi, and your prediction for the target vector, f of x sub I given W. And in set 1, we explored the notion of the bias variance decomposition, where we said that every expected test error can be decomposed to a sum of variance and squared bias. And we also spoke about k-fold cross-validation, which was this really powerful notion for how to deal with testing. So, going back over the problem, the issue is that in real life, you don't get to train your model and then test it repeatedly on your testing data, because if you test your model on said data, repeatedly, the issue that you face is that you start to hyperparameterize this new model, and you're effectively learning on your test data. But consider a situation in which you have constraints on the number of times you can apply your ML model on your test data. And this is a very realistic scenario. For example, in if you're deploying a ML model into the real world, you can't test your model on the people who are going to be using it. You have to test it internally within your training set. And so we define k-fold cross-validation, which is a way in which you could break apart your training data set into something that you truly train the model on, and then a validation set. And k-fold cross-validation was one of those methods where you split your original data set into k equal parts. You train on k-1 of those parts and test on the remaining one. And then you repeat this for every choice of the k-1 parts and average the validation errors. And the main advantage that we saw here was it is good because you're using all the data as validation as well as training to improve the estimate of the test error. Though it is true that you're also doing more computations. And additionally, we spoke a bit about model selection, about how you have a number of different models that you could try. And we also mentioned some things about the ethics of models and rules about testing and deployment. Namely, if a test set is available, you should never use it to make decisions on the model. And then we spoke about gradient descent. So gradient descent addresses a problem of how can you optimize your weights such that it minimizes the loss function. And gradient descent starts with the following algorithm. So start with some initial value, a vector W0 on either the parameters W0 equals 0, which is standard, or some random value, which is more seen as stochastic gradient descent setting. And then for for t equal to some number of epochs, you do the following. You compute the gradient, which is with respect to the weights and your input. And then you take a step in the opposite direction. So think about it as like some kind of throw, and you're walking along this throw. Every time you see an option where you can go further deep inside the throw, you take it. So really, you're kind of like minimizing some potential function. And then there's a question about, well, once you have this gradient, how much should you step? And that's this was the step size or learning rate hyperparameterizes. And we saw that if your learning rate was too large, you can sometimes overshoot what could be a good minimum. And if it's too small, it might take many more iterations to converge. And in practice, it's good to set your learning rate to be on the smaller side and increasing your number of iterations. And in set one, we also explored how convex functions have a global minimum because all local minimums are global minimums, and therefore gradient descent converges for all convex functions. And here's an example of using gradient descent on the linear regression. So your learning objective here is to minimize your squared loss, yi minus w transpose xi squared. You take your partial derivatives, and then you insert that in your gradient formula, which is given here. And here, eta is the learning rate. And the following diagram here kind of shows the behavior of this method when you apply it at various points. But a limitation of gradient descent is that it requires a full pass of the training data set at each iteration. And that is sometimes quite expensive, especially if the training data set is large. And then stochastic gradient descent, which is when your weights are set randomly, decomposes additively. So given this formula over here, so L of W, if you'll notice, is just the expected error. So here N is a number of points in your data set, and 1 over N times the summation really just normalizes your testing error. And here your gradient is just the expected gradient over single example losses. And you can then use this as an unbiased estimator for your stochastic gradient descent update. Okay. And then we spoke about support vector machines or maximum margin classifiers, which is, so in the setting of the perceptron model where you have some set of points, so here consider the red points and the blue points, and you can draw any line through it, which is what the hyperplane in the perceptron learning algorithm does. We might want to ask a stronger question, which is, how many hyperplanes can I fit in here? Or rather, what is the width, the maximum width of the hyperplane that I can fit in here? So think about this as you're trying to get in as much width as possible between your initial PLA, you're trying to fit in as much width as possible between where your classification regime would still work. And you can write this as the SVM optimization problem of what is the minimum value of W and, what is value of W and B such that you're minimizing the L2 norm squared of your weights. And this is subject to the constraint that yi, which is your target, and wtxi plus b, which is your prediction, the product of those is greater than or equal to 1 for all I. And in this problem, your margin is given as 1 over the norm of W. Then we spoke about hinge loss, which was another way in which you could achieve this maximum margin. Except now your optimization problem really has this additional factor where you're now normalizing again with respect to N. And it's kind of exactly the same setting, except your hinge loss is now defined by this parameter C of I, which is greater than or equal to the max of 0 and 1 minus the product of your target variable and your prediction variable, which is, by the way, to note a convex function. And note that SVM is equivalent to minimizing this hinge loss plus the regularization term of L2 norm square of W divided by C. And then we spoke about regularization, which is a method of making sure that you're not memorizing your training data, because your goal in creating an ML model is to create a learnable model where you're learning data to create weights. So to prevent your model from actually memorizing things, you need to kind of constrain the weight vectors. And the way we do this is just by simply setting a bound on, well, by enforcing a limit on how fast the weights can grow. And so here, the L2 regularized regression or ridge regression also minimizes lambda times the L2 norm of the weights squared. And here you're kind of trading off model complexity versus training loss, because every choice of, because, you know, if you set lambda to be very large, it means that you're really invested in how much the weights can grow. It particularly means that you don't want it to grow at all or fast. You want to stay pretty small relative to the training loss. And you should also note that every choice of lambda gives you a model class where larger lambdas constrain W to be smaller, and regularization can be combined with any loss, not just squared loss. So here are some visualizations of what LASSO or L1 regularized regression does. And here we're using the L1 norm of W. And then we have logistic loss, which is another set of loss for classification problems where you have this log weight and you have these coefficients, which are indicators that act on the sum depending on whether your target variable is truly a 1 or truly a -1. And then here the optimization problem becomes what is the weight W that minimizes the logistic loss formula, which is this equation of here. And logistic loss is also called log loss or binary cross-entropy loss, which are very popular in day-to-day machine learning scenarios. And then we spoke about multiclass logistic regression, where we'd replace the sigmoid function with the softmax, where the softmax of vectors, where the softmax of a vector A1 all the way to AK is just given by the exponent of every entry divided by just normalizing it so that the sum of everything is equal to 1. And you'll see here that the raw scores of the dot product of the weights in X are transformed into k numbers between 0 and 1 with sum equal to 1. And this kind of generalizes the sigmoid setting that we looked at in neural networks. And you can kind of see the effect here. If you have some vector X, some d-dimensional vector, you apply this transformation, you'll see that the softmax gives you this categorical distribution vector here. And then we spoke about precision and recall, particularly with mini project 1, where the question was, what are true negatives, true positives, false positives, false negatives, and then you can calculate precision and recall. And here the idea is that ML models might sometimes classify errors to be all of the same kind, but it is your job to ensure that that is not the case, because true positives and false negatives really, false positives and false negatives really should not be weighted the same way. So for instance, if someone were to have COVID, then a false positive, which means that someone who does not have COVID tests positive, that is not quite as bad as a situation in which someone who has COVID is predicted to not have COVID. Right. So it is quite important to make sure that your model is prioritizing really exactly what error type you're trying to minimize. And to do this, we have two metrics, precision and recall, where precision is a ratio of true positives to true positives and false positives, and recall, which is true positives over true positives plus false negatives. And you can combine these into a single metric, which is an F1 score given by 2 over the reciprocals of precision plus the reciprocal of recall. And the F1 score is really a score that kind of delicately tells you how much you're erring on false positives and false negatives, while telling you what your general model accuracy is. Okay, and then we spoke a bit about decision trees and bagging and random forests. So in a binary decision tree, you have some data that you're trying to classify, and you're interested in coming up with binary queries at every step to come up with a recipe to classify points. So in this setting, every internal node has a binary query function, q of x. Every leaf node has a prediction, example 0 or 1. The prediction stores at the root node, and you recursively call the query function, where a positive response goes to the left child and a negative response goes to the right child. And you repeat this process until you get to the leaf node. Your leaf node is a prediction. Okay. And the basic decision tree function class is just a piecewise static function class where we're able to partition completely over the feature space, except you're not allowed to have any diagonals. And every partition here has a static prediction, which means that in a particular region where you have a partition, you're not allowed to predict both labels of your classifier. It's either 1 or it's either 0. It cannot be both. And then we spoke about how you can determine the error of your decision tree. And we spoke about measures like the Gini impurity and the Bernoulli variance. And really the question is, what split best reduces the impurity of your decision tree? And the Bernoulli variance just measures the number of positives times the number of negatives divided by S prime. And then we spoke about bagging, because the issue is that you can always come up with a good model in which you can have a good expected value of accuracy. But the question is, how can you minimize the variance of this model? How can you get a model that gives you a consistently good score? And in practice, what you can just do is resample S prime with replacement, where you train models using each S prime and then average predictions at the very end. And bagging is also called bootstrap aggregation. And you'll see that the variance reduces sublinearly because S prime are correlated. And so, of course, more bagging means that you're reducing variance a lot more, but you'd have to, but it's a generally expensive operation, but it's still very worthwhile to do in practice. And then you can extend bagging to sampling features, where the idea is you generate a bootstrap S prime from S, and then you train a decision tree top down in S prime. So for every node, you sample a subset of features for splitting, and then you can also sample a subset of splits as well. And then you average predictions across all your decision trees. And then the question is, how can you boost a weak model? So I guess, what do we mean by a weak model? So here, a weak model is a model that is a high bias and a low variance, which means that it consistently performs poorly. So in a case like this, bagging would not work because you're reducing variance, but not your bias, which means that you're really, if your initial model performed poorly with some variance, bagging would mean that your model would perform consistently poorly. So bagging really is not a viable solution. But what we can do is gradient boosting, which is an instance of functional gradient descent for the regression case. And here the idea is that you come up with a set of linear functions, h1 to hn, and then you perform the series of operations here, which is also spoken about a lot in lecture. And we spoke about add a boost as well, which is kind of the same idea, except now you're also going to additionally weight this based on your data points. And you have these this notion of weak learners, which you can use to strengthen them by coming up with h of x that really depends on h1 to h of n, where h1 to h of n are your weak learners. And then you really keep boosting until your validation performance plateaus. And then we spoke about exponential loss, which is just defined as e to the negative y times f of x, where y is your true label and f of x is your predicted label. And we proved that AdaBoost minimizes exponential loss. And that was given as a homework problem in, I think, exercise 5. And yeah, indeed, AdaBoost is the optimization problem that minimizes exponential loss. How it works is you have d1 of x, which is 1 over n. You loop a variable t from 1 to n. Every time step, you train a weak classifier, ht of x. And then you compute the error. You define a step size, and then you update your weighting of d. And then the idea is that you return this linear combination of functions, which are now weighted via d. And the good thing about AdaBoost is that you're also kind of abstracting this notion of step size, because typically step size is a parameter that you get to choose, but here AdaBoost kind of handles some of this with constraints here. So right, and then we spoke about neural networks. So here is the neural network. You have inputs on the left, you have weights, you have sums, you have nonlinearity, sigmoid functions, and you have output features. Every layer is a parallelized weighted sum and nonlinearity. You have one sum per weighted vector, Sj equals W transpose times X. In aggregate, the nonlinearity that you observe is S is equal to Wt times X, which is a vector of sums that you get from your weight matrix. And then you can also apply H, which is equal to sigmoid of S, to get your nonlinearity. And here the sigmoid function is given by 1 over 1 plus x e to the x with negative x. It's given by this S-shaped curve on the bottom right. And then a network is a you have an input, you have many hidden layers over here, you have many weights, and you have an output. And then we spoke a bit about how neural networks kind of work. We spoke about how PyTorch kind of abstracts a lot of this detail away, but the main idea is that you have your initial data set, X, upon which you're training a model by just computing functions of what it does, comparing with a target, and then you go back and take the derivative using backpropagation, using rules that we defined in class, to re-update the weight vectors W, upon which you then redo your calculations, and then you kind of keep repeating this process until your weight vector converges. And the idea is that in your first layer, you have this S1 defined as capital W transpose X0, and the second layer is going to be W2 transpose times X1, and so on. At every layer, xi. Xi is going to be given by the sigmoid function of Si, where Si was defined here. And then you keep performing this procedure until you get to your loss, and then you backpropagate. And the backpropagation differential equation is given by this over here. And you'll notice that the loss given as a function of the weights, the derivative of this, depends on the nonlinearity here. And yes, this is kind of an intuitive picture over here, and I'd really direct your attention towards the lecture recordings for a more detailed explanation of what's happening. And for a full network, you can also draw a full dependency graph, and you can use the chain rule to get your final loss function. And then on the topic of training a convolutional neural network, usually for the purpose of image classification, we have the problem of, if I have an image, how can I classify it? So here is a bunch of images of Professor Yisong, and you'll notice that they're all shifted in translation. So some of them show his face in the middle of the screen, some of them show him at the bottom right or top left. But the idea is that all these pictures are Professor Yisong. So what's really changing is like the quality / orientation of the picture. But if a machine learning model were to train on a bunch of faces, then regardless of which of these images it looks at, it should always say that this image is Professor Yusong. But that is not necessarily the case when you naively train a model on a data set. So sometimes it's good to include further data, which means for every data set, you add some translations, some shift invariances. So you rotate it a bit, you add some noise, Gaussian noise, or you translate it a bit, and then you feed this augmented data set to your model. And statistically, these models tend to perform better because they have more regularization, which means that they're less likely to memorize, and they truly have to learn now, especially if you're constraining weight vectors. Okay, and here you have filter weights. So we have a matrix, 0, 1, 2, 2, 2, 0, 0, 1, 2. This represents a filter, which you apply on a matrix to get a submatrix. And a relevant theorem is that the only linear and translation equivariant operations are convolutions. So what this means is that you have filters which you apply onto an input feature map to get an output feature map. So during the live version of this recitation, I asked a pop quiz, which is if you use stride equal 1, padding equal 0, then how many filters are there? The answer to that was 36. What size is each filter? I believe that one was 16. And then what is the output filter map size? That's 3 by 3 by 36. And then we spoke about changing scale. You have effects like pooling, where pooling locally aggregates values in each feature map. So here you'll notice that the effect from this matrix on the left to the one on the right is that you're just choosing the maximum pixel value in every segment. So here it's 5, 8, 2, and 4. You have methods like downsampling and invariance that we discussed in lecture. You can do other operations such as maximum and average. And then we spoke about stride, which is where you define how many pixels you shift your filter by on each time. So on stride equals 2, you're computing a standard convolution, but only in odd positions. So you start at the first pixel and then you move to the third pixel and so on. So you're doing the operation on every single pixel. And then we spoke about the algorithm for k-means clustering. So this is the EM algorithm where the learning objective is, can I find communities C1 to CK or clusters, and then cluster centers, little c1 to little ck, such that you're minimizing the sum of k time, the sum of k of the sum of every x in the community ck of the norm of x minus little ck squared. So the idea is, can you come up with k-efficient clusters such that you're really minimizing node distances here? And the EM algorithm says, well, sure, you can do this. Your first step, estimate CK, which is your communities, estimate cluster membership, which is which points X go in which communities, C1 to CK. The M step is then you estimate little c, little ck, which is the cluster centers, and then you estimate model parameters. And then you derive a loss function, and then you retrain it again until you converge on something, where in every time step you modify your weights. And then we spoke about PCA, which is the question about whether if you have a data set in n dimensions, how much of this data set can I summarize in as few dimensions as possible? So in PCA, the question asks, can I summarize this data using one feature? And the idea is that you can project this data onto the real numbers using the covariance matrix, U transpose U. And you can look at the eigenvectors, which are the principal components. And you'll notice that these eigenvectors are all orthogonal to each other. So you can then arbitrarily pick as many of these vectors as you want to represent the data. And I think in practice, usually like 3 orthogonal vectors represents about 98% of your data set. But of course, you can come up with many counterexamples for this. And this works with arbitrary subsets of columns of orthogonal U. So the formal definition of PCA is you have a matrix X, which is given by real valued concatenation of n real valued vectors of dimension D. So M is a D by N dimensional matrix. You have a center for this matrix, which is given by X minus the mean of every vector. And then you have X times X transpose, which is a symmetric matrix now. And you can write this as U lambda U transpose, where U is an orthogonal matrix and lambda is a diagonal matrix. But you should note that this is very similar to the notion of singular value decomposition, where V is equal to U. So note here that this makes our understanding of PCA now amenable to what we know from singular value decomposition. The idea is that SVD operates on XT as opposed to X times X transpose. And there is a clear equivalence between SVD and PCA. And you also had the chance to explore this in homework 5. And then we spoke about latent factor models and non-negative matrix factorization, where the problem was if you have a matrix, if you have a data set, Yij, and for any fixed lambda that parameterizes the problem, what is the minimum of lambda over 2 times the Frobenius norm of U squared plus the Frobenius norm of V squared plus the sum of ij's of Yij minus U transpose Vj squared across all UV. And we said that if we knew V, then we could just use linear regression to learn U, where we treat V as features. But on the other hand, if we knew U, then we could also use linear regression to learn V, where we could use features. And so we defined this method of alternating optimization, which was, how about we do this? Initialize U and V randomly, and then we loop over the following idea. Choose a UI or a Vj, and then you solve the optimization problem for the other variable. So in this case, you solve the optimization problem for UI equals lambda ik plus the sum of wij, vj, vj transpose inverse times the sum of wij, yj, vj. And then we can now compare SVD and PCA versus NNMF. So NNMF is non-negative matrix factorization, which is the problem of if you have a matrix X, can I find a U and V such that X is approximately equal to U and V? And can I find this using as few basis vectors as possible? So NNMF finds the best set of non-negative basis facies, where it's a non-negative matrix, so you have non-negative coefficients, and they are usually orthogonal, so non-overlapping. And it's quite easy to visualize this using standard methods like SNS heat map. And SVD or PCA, on the other hand, they find the best orthogonal basis faces, and the coefficients are allowed to be negative, but sometimes this may not have a physical basis, especially if you're doing machine learning with chemistry. But PCA has a couple of benefits. You can create better reconstructions with fewer basis faces, and you can capture really an arbitrary amount of variation. And you can also quantify this variation. And then we spoke about tensor factorization. So a lot of data sets these days are represented using tensors, and it's really the norm. So if you have a m by n by q tensor, we spoke about how you can factorize this into these tensor bases of size m by k times n by k times q by k. And this gave rise to our notion of the trilinear model, which was now, can I do predictions via the three-way dot product? So particularly, what is a value of u, v, and w that minimizes the optimization problem of lambda over 2 times the Frobenius norm of u squared plus the Frobenius norm of v squared plus the Frobenius norm of w squared plus the sum across all I of the loss function of yi and this three-way dot product of utz, vtx, and wtq. And of course, there are many applications of this in online advertising where you have things like a user profile, an item description, and a query. And the question is, how can you optimize the setting? And then we spoke a bit about embeddings. So for a locally linear embedding, you can define the relationship of each x to its neighbors, say d dimensional. you find the lower dimensional U that preserves the relationship. So say k dimensional, so where k is less than d. And usually the question is, can you embed onto a higher dimension? Can you embed into a smaller dimension? In practice, if you're embedding onto a higher dimension, you're trying to find things in your data set upon which you'd like to classify things further. But also for data analysts, it's nice to embed down onto fewer dimensions to visualize your data set and visualize based on clusters, and methods like PCA or t-SNE kind of work on these dimensionality reduction techniques. So let's talk about our approach for LLEs. So you have a neighborhood. So for each data point xi, select b nearest neighbors, find weights wij, to reconstruct xi using linear combinations of neighbors. So xi is approximately equal to the sum of wij xj. And then lower dimensional embeddings, ui, are also reconstructed by wij via this notion of ui is approximately equal to the sum across all j's of wij times uj. And then we spoke about probabilistic models. So in a standard probability notation, you have this idea of p of x and y, which is denoted as p of x comma y. Your marginals, p of x, which is the probability of x happening, and then your conditional, which is the probability of y occurring given that x has already occurred, which is denoted by p of y vertical bar x. You have your rules of probability, which is the probability of x is given by the sum of the joint distribution across all y's. So intuitively, you can think about x and y, p of x and y being like some kind of table of probability. So x here, y here, and then the probability of x, y is the x row, y column entry. And then the sum rule just says that the probability of x is just when you're summing across all the rows. So you're just summing across every possible y. The product rule tells you that the probability of x and y is a probability of y given x times the probability of x, which is a classic conditioning rule. So which is more commonly written as probability of y given x is equal to probability of x and y divided by probability of x. And then for independent events or independent random variables, the probability of x and y is equal to the probability of x times the probability of y. And in the naive Bayes algorithm, let y be the classification target and x1 to xd be a set of features. What naive Bayes does is it assumes that all features are conditionally independent given y. So what this means is that you have a vector x1 to xd, and you're assuming that every entry in this vector is independent of the other entries in this vector. In this case, the probability of x and y is written as the probability of y times the product of the probability of xi given y for every xi here. And this only works because you're assuming independence. It is called naive because we're ignoring possible dependencies between the features. And then you can do some statistical inference on the naive Bayes algorithm. So here the probability of y given x from the classic Bayes rule is the probability of x given y times probability of y over probability of x. We can expand on probability of x given y as probability of as this product that we defined in the earlier slide. And then we know that this is just proportional to the probability of y times the product of the probability of xi given y. And these are the two model components that we want to learn. And then we spoke about the hidden Markov model, which is really this kind of setting where you're trying to come up with emission probabilities for every vector of possible emissions. So what you do is you have an initial state y0, you have some data that you've learned, and then based on this, you want to kind of come up with a generative setting, which is what is the probability of every emission that is possible, and then you want to sample from these emissions. And then you want to factor in what you've outputted into your current state, and then recalculate emission probabilities. So these transition probabilities here measures how the state changes over time. It's given by the product of the probability of yt given yt minus 1, which just implies that it's kind of like a Markov chain setting where you're looking at the probability of your state that you're about to deliver given the state that you have just delivered. So this implies some kind of memory inducing nature for this model, which means that you're not really just spewing some garbled words every time. There is some degree of continuity of whatever it outputs, and you had a chance to explore this as well in set 6/mini project 3. And we find these transition and emission probabilities. So transition probability describes how the state of the system evolves. So when you output a new yt plus 1, you can define your transition probability as probability of y of t plus 1 given yt. And for this, you have these variables, st plus 1, which is defined as st plus vt times delta t plus ns, where ns is a Gaussian with sigma s, and nv is also Gaussian on sigma v, but here vt is equal to vt plus nv. And then your emission probability is what you measure and how much noise you're adding to this measurement. So that's usually given by xt is equal to st plus n naught, where n naught is also some Gaussian. And then we spoke in lecture about discrete hidden Markov models, which is, here's the classic examples. Every day, Bob performs one of 3 activities: walk, shop, or clean. And then the choice depends on whether it is yt equals rainy or sunny. And then let's say Allison does activity xt and wants to infer the weather yt where Bob lives. And this is a classic application of a hidden Markov model. So in summary, you have this forward-backward algorithm where your goal is to compute the marginals, the probability of yt given x given the observed data. So based on the network here, you compute the forward messages, alpha t, where you start from the beginning, and then the backward messages, beta t, you start from the end. And the probability that yt is equal to a given x is proportional to alpha t parameterized by a times beta t parameterized by a. And usually you have to normalize these results, so that is a probability. So the EM algorithm in general has a goal where you want to maximize the likelihood, p theta of yx, but you do not know y, which is your vector, y1 to yt. So in this example, let's say you have a mixture of Gaussians. So xi is a data point, yi is a cluster to which the ith point belongs to, and theta is your cluster centers. So your solution is the following. Start with an initial guess of theta, and then use the forward-backward algorithm to predict the expected yi given x. So you sample yt given p theta of yt given x. So here you have a mixture of Gaussians, and you assign each point xi to the most likely cluster. And then you have a maximization step, which is pretend that the predicted yi's are the ground truth, and then update theta to maximize the likelihood of p theta of yx. And then you go back to step 2, and you repeat it until theta converges. So you'll notice that this is actually quite similar to the notion of alternating optimization, and it's because it is. The idea that you're really fixing you're fixing theta, and you're fixing yt, and then you're going to keep fixing one, optimizing on the other, and then alternating this until you have some convergence. And this is pretty much all I wanted to cover for today. So yeah, feel free to ask questions on Piazza and shoot me emails for questions on this. And of course, feel free to refer back to the lecture notes and lecture slides. Good luck for the final exam.